So I guess we can start again. So as I was just discussing with some people, let me end this on a couple of practicalities. So in the Google Drive, you can find the notes, including today. I'll have an update shortly after I'm done lecturing, and I will keep that material available until the end of the year. So make sure to download that. And then at least the chapters from the book, I remove them because I don't want to have any copyright problem with the publisher. And since the chapters of the book I put there are regarding the part I will cover today and some of the concepts which I covered yesterday, please let me know what you think since we are in the process of writing the book. You know, your feedback is greatly appreciated. So yeah, let us know also on behalf of the other authors of the book. Okay, very good. And so let me also start by saying, thanking one more time the organizers and also you for the opportunity to give these lectures. It has been a lot of fun. I have seen that you have taken this very seriously, and not only that, but it also has been a very positive, convivial atmosphere, which I greatly enjoyed. It was first time for me lecturing at Leches, and yeah, it was a lot of fun. Very good. And I should also mention that as I will leave shortly after the end of this lecture, there will not be time for me to have a Q&A today, but please don't hesitate to contact me, send me an email, and if you have questions, I will answer your questions. We can even schedule some time on Zoom if you like. Okay, and of course, thank you very much for being accommodating with respect to the need for leaving a little bit early because of the strike. Okay, very good. So at this point, where did we leave yesterday? I introduced the expression for the double copy and remarked on the properties of this object in terms of being interpretable as amplitudes which have invariance under linearized diffeomorphisms and therefore can be interpreted as amplitudes in some gravitational theory. Now I would like to explore a little bit further some of the aspects of this. And I will start on the gauge theory. So what are the implications of this color kinematics duality for the gauge theory? Just for definiteness, let me remind you that there was this organization for amplitude based on a set of cubic graphs. In the sense that the contact diagrams of Yang-Mills was absorbed by having numerator factors which have a piece proportional to the inverse propagator and therefore have a contact term which is accounted for in that way. So writing the amplitude for the Yang-Mills theory in this way, it was the starting point for our analysis. However, now we know a little bit more, right? So we know, for example, that we can express CT as minus CS minus U, so color factors obey Jacobi relation. So we can, in principle, rewrite this thing in the following way. So up to then the overall normalization, we can have that we can now collect the color information and try to relate these objects here, these elements of the presentation of the amplitude, from which the construction is based to our good old partial amplitudes. So we have CS, and then there's an S. We choose here to express the CT in terms of the others, and we have here NT divided by T. In a similar way, we have CU and U expressed in this way. Okay, very good. So now the following observation, I would like to make the following observation that this object here, sorry, without the color factor, is actually interpretable as interpretable. This is the partial amplitude 1, 2, 3, 4. And in order to notice this, what I would like to do is to just re-express the color factors in our trace spaces. So repeating some of the steps that we have done in, I believe, the second lecture. We express CS in terms of the following ordering for the traces. So we have 1, 2, 4, 3 minus trace of 1, 3, 4, 2 plus trace of 1, 3, 2, 4. Sorry, 1, 4, 3, 2. Okay, very good. Now there is, if you really like to have self-consistency throughout the notes, I have to point out that there's a sign in here based on the definition of the contractions of the two structural constant, which I have put in the second lectures, and here there is the CU, which instead we have used here, which again was obtained by cyclic permutation from the CS, picks up a sign. Okay, this would be 1, 3, 2, 4. This sign is important for what I mean, one has to be careful about keeping the signs straight in that. Okay, very good. So we can see now that just with this information, we interpret various objects, some of this combination as the partial amplitude. And of course, you know, the interpretation of this as the partial amplitude 1, 2, 3, 4 is based on the fact that these are all the traces which gets generated, and the 1, 2, 3, 4 appears only in this particular case. Okay, very good. So using this, but on top of that, we can also assume, in a sense, that, or verify, because I gave you explicit expression for this, we can use the same relation for the numerator factors. So this would be ns minus nu, as used before. So if we use this relation, and then we have interesting expressions for the partial amplitudes. The 1, 2, 3, 4 is equal to ns divided by s plus ns divided by t. So this is plus and nu divided by t. Whereas here we have a second expression, 1, 3, 2, 4. And keep in mind that this is the two independent partial amplitudes after we take into account either photon decoupling in this particular case or Kleist-Coif relations. So this is, everything is expressed in terms of two numerators, nu, and then there is ns. 1 over t, yes. Very good. Okay, questions about this? Yes. Or the C or the N? Yes. So in this particular case, I mean, color kinematics, it is something, it's a highly non-trivial statement, so it doesn't necessarily get spoiled with masses, but needs to be verified in that particular case. So we are assuming that we're having a presentation of our amplitude, which has that property. In this particular case, we are focusing on massless Yang-Mills. Yeah. Yes. No, so we are using the particular kinematics in this particular case. I mean, of course, you know, this is a relation which holds in the dimensions. So you can, in principle, just model masses as compact momenta. just say write your theory, I don't know, in 5 dimensions or in 6 dimensions, and then you consider some fields which have compact momenta. These behave like masses. Color kinematics duality would not be spoiled in that particular case. But so for this simple example, I would just focus on massless fields, and of course the kinematics is part and will be used actually in a second. Other questions about this? So keep in mind that this is, I mean, that is just group theory, Jacobi relation. This is the highly non-trivial statement. Of course, if we are at 4 points, in a definite theory, I gave you the numerators which obey this property. There's construction for Yamils up to 1 point, in some cases using string theory. So at 3 level, this is a property of Yamils which is established. Loop level, it is still has a conjectural status. And it is difficult to find, I will remark on this later, but it is in general quite difficult to find representations of amplitudes which obey this property. And also keep in mind, just as a reminder, that this is a property of a presentation of amplitude. You can have the same amplitude in a way in which the duality of this property is not manifest. Okay, other questions about this? Otherwise, I would like to actually rewrite the same relation in a matrix form. So we have expressed 2 partial amplitudes. Again, these are the 2 partial amplitudes which are independent after we are using the KK relations, and we express this in terms of 2 numerators. And one property that is quite interesting here. I mean, so far it's the same relation rewritten, but then you can look at the determinant of this matrix. So let's give it a name. Let's call it B, since M will be for the amplitude in gravity. And you have that, the determinant of B. Well, it's a short calculation. This is, of course, we can write this as minus 1 over T plus 1 over S, 1 over T plus 1 over U, and then there is plus 1 over T squared. You rewrite these terms as there is minus Ts, this would be U, using, I mean, we are using heavily, as you were pointing out to the fact that we are having massless kinematics, and this would be minus S divided by Tu, so you have some cross simplifications, and you can see right away that this minus sign and this plus sign gives you a 0. So in other words, this matrix has a 0 eigenvalue. If you think about this, it needs to be so for a following reason, or at least I have heavily anticipated this will be the case. Whenever I introduce numerators, I told you that these are not gauge invariant objects. And in fact, I just emphasized before the fact that this is a property of a presentation of the amplitude. In other words, you can do some form of gauge transformation, generalized or not, which changes the numerators without changing the amplitude. Whereas with the partial amplitudes, I try to emphasize the fact that they are gauge invariant objects. So it would be, in a sense, a problem if I can find an expression for an object which is not expected to be gauge invariant or physical by itself in terms of the physical object. So in other words, this is there are relations here which are implied, which needs to hold among the partial amplitudes for this to be possible. Okay, so the best we can do then, since we cannot express our numerators in terms of partial amplitudes, the next best thing which we can do is to just express them as, for example, one partial amplitude and the other numerator. So let's try to do this. This is just an immediate rewriting of the first relation up there, in which we have just used again the kinematics property again, and then we just substitute this expression for a new inside the other expression that we have, and the final result would be that the expression for a partial amplitude 1324 is equal to S over U, the other partial amplitude. So in other words, at 4 points, we do not have in Yang-Mills two independent partial amplitude. We have just one. This relation came as a surprise historically, what historically means 2008-ish. It was long believed that Yang-Mills amplitudes would just have n minus 2 factorial independent elements, but this is just the first sample of a relation that also holds a higher multiplicity, and this reduces the number of independent partial amplitude for that particular theory. There is a way of rewriting this in a slightly easier form. So, yes, it is known that for Yang-Mills, it is an endpoint statement. It is an endpoint statement. And you can see this, I mean, if you want to think in terms of string theories, you can see this as a consequence of string monodromy relations. Okay. So another way of rewriting the same relation, which makes it easier, in a sense, to memorize or to understand what this is, it is essentially a sum over partial amplitudes in which we are having one of the legs or of the elements which changes position, and in this particular case would be leg number 3, and then we take the scalar product of that with all the states which are placed before that. So in this particular case is K3 scalar product K1, and then we have another element in which we have, say, K1, say, plus K2, scalar product K3, and this would be A4 of 1, 2, 3, 4. Okay, and this would be a 0 in the end. So essentially, like the 3 is moving around, and I multiply each terms of these relations by the momentum associated to the leg which is moving around times all the sum of all momenta which are on the left. And of course, you can see that the other two amplitudes which are missing, considering all possible ways of inserting leg number 3, come with coefficient 0 because of this. And this is the pattern which you can see at higher points. We call these BCJ relations. Okay. Very good. And you can think, of course, that this corresponds to the 0 eigenvalue of the matrix at 4 points in that particular case. Yes. Yeah. Yes. A short comment. I do not know how much I want to say. So after, okay. I do not know if it makes sense to go for an aside, but let's, okay, so these were first discovered in field theory, but then after that, of course, given the close relation between some of these constructions, including KLT that I was about to explain to you, with string theory, people started looking for a string theory origin for this. And so the simplest way, this is probably a remark I wanted to do at the end, but let me just, I'll be slightly schematic in here, but, you know, as an aside. So let's consider some amplitudes in string theory, open string, and let's consider amplitudes we're talking about open bosonic string, tachyonic amplitude, which we know they are on physical undergrounds, but they have they are the simplest amplitude in that they have the basic analytic structure, which also more physical amplitude share. So let's consider the simplest example, of course, is tachyons, 4-tachyon amplitude. So I recall, and you have seen this in the course, that these amplitudes are typically, let's say, let's consider the ones dressed with a certain, with a specific trace, and they are expressed. They are first obtained by fixing the positions of some of the poles, right, on the worldsheet, which are on the boundary. Here schematically, I represent this as the disk. So there's going to be one at 0, one at 1, one at infinity. And then there's going to be, the other one is not fixed, right? It's integrated. So we are having, it's good to put a color in here, an integral, which goes traditionally or I don't know, conventionally from 0 to 1. And so this, I mean, let me just say, proportional to this integral, and then you have x to alpha prime, and here we have to consider the corresponding product of momenta, so k1 and k2 are the ones, and of course, you know, I am assuming here, right, that this the puncture in position x is associated to k2, k1, k3, and k4. This is how I decide which combination of Mandelstam I have here. So the same in here. This is going to be 2 alpha prime, k2 dot k3. Okay, so this is just, say, a prototype of an amplitude. One thing you can do is to deform the contour here. Right, so what happens if you deform the contour? And you go, essentially, to this. Now we have two pieces of the contour, right? So one is going to look like this, and the other one, use a different color, from minus infinity to 0. Okay, this deformation of the contour expresses this amplitude in terms of two pieces, which naively you would interpret that as partial amplitudes, as coming from a different ordering. Less naively, you realize that as you do this deformation, an extra phase is picked up. Okay, so in whichever tools, I mean, in whichever formalism you want to do string amplitudes, you can try to do this simple deformation. And for this particular example, you get a simple relation between three amplitudes. Perhaps you start from expressing a 0 just by having a trivial loop in here, and then you expand that and you express that as the sum of three terms, each involving one of the partial ordering. In any case, this is the relation that you would get. And you would have some phases, which are 2 pi I alpha prime, in this particular case, k2, dotted into k3, a1, 3 to 4, and then there would be 2 pi I alpha prime, and here k2 dot into K3 plus K2 dot into K4. And this would be A1, 3, 4, 2. And this would be equal to 0. So this is a simple example of a relationship which looks very close to to the BCJ relations. The fun part of this is that, I mean, of course, field theory relations are found in alpha prime going to 0 as a limit. But the fun part of this is that you take a real and an imaginary part. You take a real and imaginary part and the alpha prime going to 0 limit, and what do you get? The real part becomes photon decoupling or KK relations. Because the exponential starts from 1, right? So there's going to be a relation there which does not involve the kinematics. You take the imaginary part, you expand the first non-trivial term there, will be, I mean, dividing, of course, by alpha prime. The first non-trivial term will be a relation which has this form. Is it the same relation? The first term would not have an imaginary part, 1, 3, 2, 4. So here we are moving around, quote unquote, different legs. So in that particular case, we were moving around leg number 2, right? Whereas here is leg number 3. So I have actually chosen the wrong, I would have to give a different version of this, but it will be the same identity. And this is an elementary example now. This stuff can arise in string theory. Okay. I hope this answers the question. I have, let me give you a reference if you want to read more about this. The original paper is Jerome Bohr, Damgaard, and Pierre Vanove. And this was also discovered or written down by Stieberger on the same year, 2009. So this is the situation. Mm-hmm. Mm-hmm. Yes, yes, it is. So this is a more general property. Yes, but if you start mixing levels, then it becomes, if you want to start considering the string masses, then you have a relation which is not exactly that, right? You start having that you need to use the relation with the alpha prime. So this is, in a sense, in that setting, the more fundamental relations, if you want to think in terms of string theory, of course. But also, this is an indication that this is not an accident of massless theories. But there is a property there which is general, well, general, I mean, it is characteristic of the string theory. So yeah, don't think about this as a property of massless theories. There is something there, but it's not exactly copy and paste if you want to do massive theories. Okay, very good, very good. Other questions about this? All right, so I went slightly off the tangent, but I think it was a very good tangent to take. Now I would like to give you, I want to say, if you want to tell the story at the elementary level at 4 points, which is the simplest non-trivial example, but also an opportunity to learn a lot, there's one little piece which is missing. Namely, now we have a good way of expressing our partial amplitudes in terms of numerators, and so I would like to have the double copy property, right? Because everything you see here is in Mills. So I would like to express gravity using the partial amplitudes. Let me see, where am I allowed to cancel stuff that I want to keep. These I have some relations there. This can go though, hopefully. Okay, so with some simple, I should say, manipulations, then I would like to just consider the following object, right? We have M4. And here, there is a normalization, of course, there, and then we express this as an S squared. And just as a comment, you have seen this relation with tilde before, but what I want to do is the most elementary form, in which really I take polarization on the right and polarization on the left for the same field to be the same. So here I have really a square. Okay. So now, just the basic use of color kinematics duality tells you that you can express one of these numerators in terms of the other two. So let's try to do this, and then what we want to do is we express this in terms of DNS. So we are keeping here. We are keeping here, like, say, NS squared. There's going to be a contribution which comes from this. So there's going to be a 1 over S, but also 1 over T. We see here some of the same entries of the matrix which we wrote before. Now we have the double product between these two. So there will be 2 NS divided by T. And then NU, I express that with the relation I have up there, so that I have thankfully retained. And this would be IT 1 of A4 of 1, 2, 3, 4. This is the partial amplitude plus U divided by S over there and S. And then there is a term there with NU squared, which is 1 over U plus 1 over T. And then has the content of this bracket, IT A4 1, 2, 3, 4 plus U divided by S and S, and this would be just squared. I have to close the bracket over there. Very good. So now we just expand everything, and we just carefully keep track of the terms. So in the DNS squared part, we're going to have the following part. So I can rewrite this term as minus U divided by ST. And then I have the term coming from here, which is plus 2 U divided by ST, coming from the product between these two terms. And then also I have a term in there, which I write plus, again, I use UT multiplied by minus S in that particular case. So let me put a minus sign in here. And then I still have a term from the square, which is U squared divided by S squared. So this is everything which is proportional to an S squared. You can see right away, you can see right away, yes. You can see right away that actually this term vanishes. Yeah, plus 2, minus 1, minus 1. In a similar way, we write also the term linear in an S as there will be 2I NS T that multiplies T 1 over T. So this would be just A, the partial amplitude 1, 2, 3, 4. And we would have another term which is linear in an S over there, where we would have plus 2I, and then there would be UT minus S, which multiplies T u divided by s. So again, this is simplifies essentially that term, A4, 1, 2, 3, 4. Okay, so this is the term linear in S, which is vanishes. And we're left now with the term containing the square of the two amplitudes, the partial amplitude. So this is a term which comes, as I said, there is a minus minus ut minus s divided by ut coming from this term. And then we are going to multiply this by a minus 1, so the sign changes, and then there's going to be a t squared. Okay, and then there's the square of the amplitude. So there's some simplification here, and ultimately what we have found is that is a prototype of what is now what we will refer to as a KLT relation. So this is a relation which involves an amplitude in gravity in terms of the product of partial amplitudes in Yang-Mills theory. Times some kinematics. So in this particular case, we're going to have that M4 is going to be equal to, this is a 4 graviton amplitude, as I said, minus I st divided by u, A4, 1, 2, 3, 4 squared. So this is what another manifestations of obtaining gravity amplitudes as the square of gauge theory. Let me just do one extra thing before I open this up to questions. I would like to do a minor rewriting here. So let's try to express the partial amplitude A4, 1, 2, 4, 3. So another one in terms of the others. This is a nice exercise because that forces us to use all the relation which we have written, or some of the relation at least, or most of the relation that we have written so far. So we use first photon decoupling, right? So this is the same as 1, 2, 3, 4, and minus A4, 1, 3, 2, 4. So what we have done here is essentially moving leg 3 around, right? So we have 3 in this position, 3 in the other position, 3 in the last position, minus sign because yes, you remember how the photon decoupling identity was written. Very good. But then we express this, the first piece I'm happy about. The second one, 1, 3, 2, 4, 1, 3, 2, 4, we have the 1 over there, right? So we can express this as minus 1, with an overall minus sign, 1 plus s divided by u, and then the only one partial amplitude, 1, 2, 3, 4. Thereby, in a sense, corroborating the fact that, of course, we have just one independent amplitude. Everything else can be expressed in terms of this. But this is the same as t divided by u, A4, 1, 2, 3, 4. So another expression for the same relation would be, which is the most common expression. I mean, if you look for KLT, you'll find a simple kinematic dependence, just the s variable here, an overall phase which really depends on who is writing the paper, because different conventions are there in the literature, and then the product of 2 partial amplitudes, but with different orderings. Okay? The general structure which we will see at higher points, well, the general structure which is there at higher points, but I don't think you're going to see it today, is this. So some kinematic dependent metrics multiplying partial amplitudes with a different ordering. And what should be remarked at this point is that the way of writing these relations is highly non-unique in the sense that there's a lot of relations that partial amplitudes obey, and by using those, you can rewrite in a number of ways the KLT relations. Okay, very good. So this is a highly anti-historical introduction in the sense that KLT relations were first observed in the 80s. And historically, this is a big part of gravity is the square of Yang-Mills theory, where it's coming from. What I have provided is an introduction based on BCJ, the BCJ construction, simply on the account that the BCJ construction is exclusively field theoretical. But it's important to understand that it came with some guidance from string theory. So in a sense, we are having amplitudes in field theory and amplitude in strings that co-evolve together with a lot of cross-fertilization, I should say. Questions about this? Sure.
So, Yang-Mills, you have to have the Fermat diagrams, then in the simplest case, the level of point, you divide the contact term in order to have the amplitude in the form, let's say, roughly above the C's. Then you perform an additional improvement to go in the CK1 form, and then you see the double copy.
Yes.
Color factors or kinematic factors, and you find an amplitude in a gravitational field.
Yes.
Of course, an amplitude is a gauging variant number, so it is what it is. So on the Yang-Mills side, you would reshuffle back and write it in terms, I mean, as ugly as you want. My confused question is there any understanding of how the gravitational amplitude would look if I would reshuffle my kinematic factors, at least in some cases?
Now, that's a very good question. So I have two answers to that. So this is, in a sense, answer number one is the reason this is important is because this is gauge invariant way of writing this. So no matter how you get to the double copy, the fact that this is a formula which is easy to check, right? Because there is no ambiguity or presentation into writing this. This is answer number one. Answer number two is that you can do something almost identical to what you described in one of the two gauge theories entering the double copy. So only one of the two sets of numerators need to obey color kinematics duality, and this is something that I will remark in the last hour. So in many situations, in many practical applications, you are having a simple theory and a more problematic theory that you double copy, and you just need to have one set of duality satisfying numerators. You are still in business. But you are not in business if you have two numerators that are not. So if you don't have any single duality satisfying presentation of the amplitude, then if you are confident that still such presentation exists, this is the way to go. Because in here I have assumed that there is a color kinematics duality satisfying presentation, but I don't need to know what it is to derive this relation. So this is the best strategy. If you have one set of numerators which obey the duality, then it's a very powerful combination to have one set of numerators obeying the duality and then another set of numerators that perhaps don't obey the duality, but they have better power counting properties, or perhaps they can be straightforwardly obtained. I'm thinking a lot about the construction for n equal to 4 supergravities, in which you have on one side of a construction n equal to 4 super Yang-Mills, on the other side a non-supersymmetric theory. So you can recycle all the color kinematics duality satisfying information you have for the n equal to 4 theory, and then you can do Feynman graphs on the other one. You don't need to get to a presentation which obeys the duality on both sides. And this has been very useful, actually. Even in terms of combining partial informations on one of the amplitudes, because you want to have only the numerators that combine with non-zero numerators on the n equal to 4 side in that particular case. So in some cases, you don't even need to have a complete representation of the amplitude for the n equal to 0. You just need to have the piece of the amplitude that combines with n equal to 4, and you have the n equal to 4 supergravity amplitude. Okay. Another thing which I wanted to remark, and then we take 10, 12 minutes break, is the following. Say that I give you a mystery theory, right? It may be difficult to obey, to find the numerators that obey color kinematics duality. A consequence of color kinematics duality being the BCJ relations, these are easy to check, okay? So if you do not know whether your theory obeys that property or not, but you have access to the amplitudes, this needs to be true if the theory admits color kinematics duality numerators. In other words, this is a situation where checking is easier than constructing, say, the ends in an explicit way. Okay. Let's take maybe a 10, 12 minutes break. Please come a couple of minutes. Okay, very good. So we are now in the position to continue. Just one last remark. So I want to remind you the fact that the pairing of the polarizations is quite important for the construction of the double copy, and in particular, you can obtain, by just combining at 3-level amplitudes from 2 Young-Mills theories, there's not just gravitons. You're going to have, as I think I mentioned before, also in 4 dimensions, at least a complex scalar. In the dimension would be an antisymmetric tensor and a single scalar, which corresponds really to the decompositions of, according to the little group, of the product of 2 polarization vectors. So in other words, another thing which we can learn already at 4 points, already in an elementary example about a double copy, is that you get a theory of gravity, but there will be some extra stuff. Now, if we just care about 3 levels and graviton amplitudes, we can always just consider graviton amplitudes. And of course, if you start having gravitons, only gravitons on the external lines, you're not going to have any scalar propagating. But this will not be the case at loop level. So if you want to consider the same result at loop level, then you need to either project or come out with some other method for canceling the contribution from the extra fields, or perhaps you're just declaring that you're not interested in the amplitude in Einstein gravity, but you're interested in the amplitude of Einstein gravity plus a scalar field. The only important thing is that you understand what theory you're doing the calculation on. And I think you have a very good understanding of this by now, in the sense that I presented to you the double copy as a linearized diffeomorphism gauge invariance satisfying constructive techniques. So you know that you're constructing amplitudes with that property, but that doesn't guarantee alone you to get the theory which you're desiring. Of course, if you add extra properties like a lot of symmetry, like n equal to 8 supersymmetry, then you know that you are landing in a theory you can identify and is unique. But that is not the case if there is less symmetry. Okay. After this remark, I would like to spend the last 40 minutes I have into making some statements about the double copy in a slightly more general setting, learning based essentially from what we have learned at 4 points. Yeah. I wouldn't say that. So I would say, okay. So, okay, so if you want to create a theory that reproduces the amplitude of Einstein gravity, there's essentially 2 avenues for doing that. One is projection. So you would say, well, it's not a theory. You can do operations on the output of the double copy, right? If you just care about the amplitudes. Another one is a slightly more subtle construction, namely introducing some ghosts in the theory that eliminate the states in the loop which are unwanted. And this is, if you want a reference for that, it would be Henrik Johansson and Alex Ochirov have worked on this, I want to say 2014-ish. I can send you, if you like, the exact paper about that. And what they're doing essentially is studying the double copies in the presence of matter. And then you can choose whether you want to have extra states in your theory, so perhaps a more general gravity theory, or you want to use some symmetry between the extra matter and the states which are coming from the double copy of two gluons to sort of remove the states from the loop. So if you ask those people, they will tell you, yes, absolutely, the single copy of Einstein gravity is known, and there's this this theory with ghosts. There is, I mean, I'm slightly more neutral over that. For me, this is mostly a way of constructing amplitude, so you can construct that in that way, or you can project, whichever is most convenient computationally works. But I think there is something to learn about the double copy here. The fact that your physical intuition about the gravity theory should not guide your selection of the gauge theory necessarily. You can have a very pathological gauge theory, which nobody in their right mind would ever consider as a gauge theory, do the job of reproducing the amplitudes in gravity. In this particular case, it is a gauge theory which has ghosts into it. And I want to emphasize, these are ghosts, not like the ghosts you're normally using in Ian Mills to have a BRST quantized theory. We are talking about the ghosts which are like states with the wrong statistics. And they are just moving around as physical states of your theory. The gauge theory is pathological, but the output of the double copy is not. Okay. Other questions about this? So let me try to give you at least the language to have at higher points and loops. So part of the advantage of the double copy formulation I have chosen is the fact that it is straightforward, at least to pose the same questions at loop order. What do I mean with that? Well, that numerator factors and color factors are objects that are much easier to generalize to loop order. So a loop level amplitude will be a situation of this form. So we have a summation over cubic graphs. This corresponds to what we have seen in terms of dividing up the amplitudes for points just in 3 graphs, with each with a channel, and sort of assigning contact terms to different cubic graphs. That is the same element in here, and now we have a certain power of loop momenta. Sorry, a certain number of loop momenta. We are in D dimensions. There's going to be a symmetry factor, which is the same as in a Feynman diagram. And then we have, again, our numerators and color factors. And here there's going to be a product of propagators. Okay. The propagators are the same as in the scalar theory. Some people like to talk about an auxiliary scalar theory whose job is just to provide the correct propagators. In some cases, people even talk about bi-adjoint scalar theories in which you have 2 copies of the color factors, and then you have a triplet of theories, 1 gauge, 1 gravity, and 1 scalar that sort of are related by these constructions. And then the basic elements here is that you will find, you have a lot of color factors, and then you will find color factors which are in triplets of this form. Now you have a lot of, we're considering adjoint fields for now, although I'll say a few words on how to generalize this to more general theories. And then we are going to have color factors, which are strings of structure constants. This is just an issue of normalization to use the tilde ones, but this is the standard normalization, which was used in this formula. So if you want to get the part proportional to the coupling constant right, you need to have this. Okay, BD. Sorry, AC, AD, DB. And then there is, let me just be consistent with my notes, there's a third element, which is a C2 DA E F tilde E BC. And again, with dot, 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 I indicate other pieces of color factors obtained by multiplying structure constants, which are the same in all cases, right? So if I want to use the Jacobi relation, now I will have, this is a slightly different sign convention for the Jacobi relation. Here, there would be 1 plus and 1 minus signs, which in turn depends on how I have placed the indices for these color factors. This is just a Jacobi relation. So we just have more color relations stemming from Jacobis at higher points. And graphically, I can represent this in the following way. We are going to have some subgraphs in this. Let me just, I will explain in a second. So there's going to be that, and then a minus sign. This is the one difficult to draw. So we have D, C, and then B, A. And we have now considering this is no longer 4 points, so we are considering these as subgraphs which exist in larger graphs. These graphs can have loops, if you like, and as many external lines as you like. So the idea is always to find sets of graphs who have color factors related by Jacobi relation corresponding to a subgraph. There can be loops in here. I want to be very, this is a minus sign. There can be loops in there, so I want to be very general about this. And this will be a prototype of a color relations expressed also graphically. And now color kinematics duality is still the same statement. The color kinematics duality implies or posits that whenever I can find a color factor which is expressed in terms of other color factors, an algebraic relation, then the same algebraic relation can be imposed on the corresponding numerator factors. In a technical part is also that when we are saying that we impose the algebraic relations, the same algebraic relations on the numerator factors, this also includes symmetry or anti-symmetry in flipping of some of the indices. So for example, keep in mind that when you have a 3-point amplitude in Yang-Mills, you have an anti-symmetry property in both color and numerator factor. This is also what you want to keep imposing. In some cases, however, we'll have that not all lines are the same because we have a representation other than the adjoint, but here in this example, we just consider adjoint fields. Another technical part is that when you are imposing this on the numerator factors, you are keeping the momenta here fixed. So you are keeping the momenta for 4 external lines, not external lines, but for 4 marked lines in here, which now are internal lines, so they will depend, say, on loop momenta, for example. So by imposing this numerator factor more in detail, they will be functions of external loop momenta. And while you're imposing this relation, you'll do that at values of the loop momenta such that the marked lines are the same for all triplets of relations. So this may imply a shift of the loop momenta in some cases. And in this line here, shall we say, the red line will have obviously different value of momenta in the three cases. Okay, very good. So we see in a sense that this Jacobi or or dual Jacobi identities, they are a local operation on the graph in the sense that they involve only one particular internal edge. And that's a part of it. Okay, so if this is the setup, then amplitudes in gravity, in a gravitational theory, can be obtained by as a double copy. There is here, in general loop level, we have a slightly different normalization. There's an L+1 replacement of the coupling constant by kappa divided by 2. And then there is the same summation over cubic graphs, the same integral over loop momenta. Same symmetry factor, everything is the same, except that as the double copy suggests, we are replacing the color factor by a second copy of the numerator. Okay. And for some reason, this will be a summation over J, as it is over J. And again, cubic graphs. Okay. Very good. So again, a question which should be asked is what gravitational amplitude are we obtaining? Probably the best known examples are n equal to 8 supergravity being the double copy of n equal to 4 super Yang-Mills with itself, and gravity plus a scalar, which some people call n equal to 0 supergravity for some reason, being Yang-Mills times Yang-Mills. There's many examples in the literature, and sometimes we use the word of web of double copy theories. Here I would really like to refer you to the review we have written for a lot of examples. But it should be mentioned that in many cases, this is still a topic of current research, and there's a lot of work to be done in terms of finding gauge theory factors which give you your favorite supergravity theory. Okay. One thing I want to emphasize, well, first I'll ask you if you have questions about this. Yes? Yes. Yes. Okay, so what is not proven is at loop level the fact that we can always find numerators that obey color kinematics duality. At 3 level, there's constructions. So at 3 level, this is proven. But at loop level, there are constructions, but the general statement is not at the proven level. For general loops, of course. And computationally, the hard part is this. Of course, gravity is a complicated. Writing amplitudes in gravity is not easy, so the complexity goes somewhere. There's not such a thing like a free lunch, right? So the complexity is in finding presentation of the amplitude which obey this property. And one thing I want to remark, particularly for the ones among you who are perhaps interested in actually using this for construction, is the fact that in many cases, the numerators which obey the duality there is a tension sometimes. Explicit presentation are difficult to find, And sometimes locality, crossing symmetry, or diagram by diagram power counting conflict with the duality, so to speak. So perhaps you have to put, I mean, concretely, perhaps you need to have presentations of the amplitude in which crossing symmetry is not obvious at the level of the individual numerator. Of course, the amplitude will have crossing symmetry, but that's something you sacrifice in finding the presentation. Some legs play a better role, a different role than others. Sometimes you need to allow for more loop momenta in the integrand than you would otherwise, so that the individual diagram has a power counting which is worse. Or sometimes you have to consider even non-local numerators. In many situations, you can still do a construction in which one set of numerators obey the duality, but not the other, and I will explain this in a second. I think this is one of the last takeaway messages, but in practice, this is the difficult part. Other questions? Yes. Sorry, go ahead. This is a good question. So the organizing principle is, there are of course organizing principles, and this is symmetry, right? Symmetry is always something that you use to organize your theories, and if you have supersymmetry, then you can organize your double copies by the degree of supersymmetry. In many situations, you end up landing in a unique way. There is, however, a limitation, shall we say, of what explicitly realized symmetry you can have. Namely, you can see this already at n equal to 8 double copy, right? What is the symmetry which is explicit in that case? You would need to have a manifestly realized SU8 in the gravity amplitude, but at the level of the gauge theories, SU4 times SU4, which is a lot less. So not all the symmetry will be manifest at the level of the individual gauge theory factors. There's also cases, you take n equal to 1 times n equal to 1, you get an n equal to 2 theories with extra matter. The n equal to 2 theory will be upliftable to higher dimension than 4. N equal to 1s will not, because n equal to 1 gauge theories are, I mean, in the general case, unless you have secretly writing something which uplifts to an, and has a higher supersymmetry, they'll be 4-dimensional. So in many situations, we have that the symmetry manifest in the construction is less than the symmetry of the theory. You have symmetry enhancements, and depends how you look at that. It can be very interesting, or also it can be not so nice. Aside from this, there's, I wouldn't say big organizing principle, but there's a lot of work into sort of charting the space of possible theories. And personally, I've been looking a lot at n equal to 2 supergravities. I think they are an excellent middle ground between theories which have very little symmetries and theories which are so constrained by symmetry that symmetry is the only organizing principle you can envision, and theories are specified uniquely by that. And yeah, there's a lot it can be done, but all in all, this is a topic of current research, so you should work on it. There was another question. Yes? So this is a schematic for, I mean, this is an example, yes and no. So the punchline is that color relations stemming from the Jacobi's will have this generic form for some I, J, and K. So say that I'm counting my graphs, and then I pick up the I, the J, and the K, so that they have this common, so they are the same, except that there is these 4 labeled lines that combine in different ways in the red line. So this is the schematic way of representing a color relation stemming from the Jacobi of corresponding to one internal line. Question you should ask also is that all there is? Or are there other color relations? And it really depends on what kind of theory you're considering. If you're considering a theory which has a generic gauge group, well, that's all that you're going to have, but you have to be very careful when you are when you are proving gauge invariance. that this is all that there is. If you forget to impose a numerator relations when the corresponding color relation has been used implicitly or explicitly to prove gauge invariance, you will get a theory which is pathological, or namely is not invariant under linearized diffeomorphism. So whatever this is not a gravity theory in the conventional sense. Yes. So, I mean, usually we consider higher dimensions. You need to have scattering, right? So it's, I mean, in d dimensions, you can write it down. You can have scattering states into them. It would be rather trivial, but yes. Mm-hmm. Well, sure. There's been some interesting work done, not in 2 dimensions, but in 3 dimensions, where there's anything you can do. And in some cases, in that case, people use Chern-Simons theories with matter. And there are some nice double correlation. In some cases, you have also off-shell extensions, which is a bit a very big departure from this philosophy, but people have done that, and I can find out some references if you like. So I keep telling people I find out some references. So how does this work in practice? I shall write an email with some additional references. I send it to you. You send it to everybody. Oh yeah. Okay. Okay. Sure. Fantastic. Fantastic. Okay, that makes sense. So I'll note it. I'll note that. Okay, very good. Other questions about this? So I think that we have 15 minutes left, so I don't mind having a smooth transition towards you asking questions. Otherwise, there are 2 things that I could potentially explain at this point, or otherwise they're in the notes. Thing number 1 is revisiting the argument for gauge invariance under linearized diffeomorphisms in the more general case. Thing number 2 could be actually justifying the statement that, well, you just need one set of numerators to obey color kinematics duality, not the other. And then in the notes, there's also an example about 5 points, because I want to do something about higher points, but I will not have the time to cover this. However, the 5-point example is just a couple of pages. It's something you can do in a Blackboard. So it is quite interesting. So what do you want? Linearized diffeomorphisms, or do you buy them from 4 points? Only one set of numerators obeys the double copy. Yeah, okay, that is a good choice. All right, so very good. So how do we do this? So let me start with a statement. So how do we see this? This is actually gives you also an idea of the manipulations which are necessary for showing some of the statements, also realizing in terms of linearized diffeomorphisms. So then a very important thing to remark is the fact that only one set of numerators needs to obey CK duality in a manifest way. Way or form. So we are still assuming that there exists a presentation of the numerators which obeys the duality. But that it may not be readily available. Do you want to make sure that that's actually the case? Well, check the BCJ relations. That's the easiest thing you can do, because that is a gauge invariant check, which doesn't depend on any choice. So assuming that there exists a set of numerators, then we can easily express, these are the numerators I have. These are the numerators which obey color kinematics. And this is something else. I mean, this is the difference between the two, which may not be explicit. So we think about these as generalized gauge transformations. In the sense that if you do a gauge transformation, the change of the numerator can be cast into this form. And if the amplitude is the same, then one thing which needs to occur is that schematically here I'm omitting normalizations and such. For a gauge theory, you'll have this, that the variation of the amplitude is equal to 0. Okay, so if we do the same operations on the gauge theory, the fact that these are numerators of the same theory rather than numerators of different theories implies this relation from invariance of the amplitude of the gauge theory amplitude. So okay, very good. And then there is a basic observation, the fact that the only conditions to get a 0, only algebraic properties of CI are used. Okay. So then it is immediate to verify that this amplitude here, the supergravity amplitude is expressed, or the gravity amplitude is expressed as is obtained by squaring a set of numerators that obey color kinematics duality with a set of numerators which are the ones available at the moment in a theory that I know to satisfy color kinematics duality, just I don't have an explicit presentation of the amplitude, then the double copy will be related to, will be identical, essentially, to the one where we have the tilde without the primes. Okay? Plus, the other term would be Ni, delta I. I still have the tilde, yes, the I in here. And this will be equal to 0 because the Ni have same, well, they have CK duality, or obey. Meaning that they have the same algebraic, they obey the same set of algebraic relations as the color factors. So the output of the double copy is the same, and this is the object that you can prove by running the same argument that we have done at 4-point. You can prove that this is invariant under linearized diffeomorphisms and therefore has the property. In other words, the double copy amplitude does not change in case just one of the set of numerators obeys manifestly color kinematics duality. Of course, you can see what goes wrong if you have two sets of numerators that don't obey the duality. The fact that there is a term there in which you have both deltas that is not known to you to satisfy. You cannot argue that that vanishes. Okay, this is very good. Yes? Yeah, so there is yeah, so the symmetry factor is still there. Here I have not included that. Also, I should mention one thing here, that this is at tree level. Okay, if you want to generalize this at loop level, then you use the unitarity method. Why am I saying that? Because otherwise, there's another mechanism which can make something to vanish at loop level, namely integration. It can integrate to 0 without being the consequence. So this is at tree level. And there is no symmetry factor. Now, how do we argue this at the level of at loop level? Well, think about integral reconstruction in the sense of what we explained in the lecture about the generalized unitarity. Then you see that by construction, this amplitude has the integrand, because this is an integrand level construction, has the right poles which you expect. So you can argue that having a complete knowledge of amplitudes at tree level, then the double copy properties extends to loop level as a consequence of the unitarity methods. Okay, very good. Other questions about this? Otherwise, I have a couple of additional comments. So as I said, at tree level there are explicit construction. At loop level, that's the question you asked. CK duality for general loop is conjectural. There are construction at one loop. Yes. Sure. Yes. This is part of it indeed, because you can prove it, of course, on the cut by cut. When everything is on shell, it's tree level. So the big problem and the common, I mean, I wouldn't say something to. There has been suggested proofs at loop level. I don't think at the moment. I mean, I'm being recorded, so sorry. I'm going to say something different here. A possibility where things would go wrong at loop level is exactly when you're relaxing a cut condition, so that you're going, exactly as you said, from on shell to off shell. Yes. Anything else about this? I should mention also BCJ relation can be generalized at endpoints in the way that we saw. So that typically, perhaps it is worth at least putting it on the blackboard. This is this is probably the most gauge invariant way of checking that you have color kinematics duality, so the consequence of color kinematics duality. So here we are having that, as I mentioned before, this generic form of the BCJ relations will be a sum over 3 amplitudes. So again, in which we have one particular external legs which is inserted at different positions. So in this particular case, it will be inserted as position I. And in this particular case, I consider leg number 1 and I move it around. And this would be n. This is equal to 0, and this would be an endpoint amplitude. And each of these terms is multiplied by a kinematic factor, which is expressible as the scalar product of the momentum of the line which is moved around times all the momenta on the left, the sum of momenta on the left. So this is the generic prototype. This in turn, with some extra work, allows me to show that there is an n-3 factorial basis of partial amplitude, which to the best of today's knowledge is the number of independent partial amplitude you have, unless there's a very big surprise somewhere out there. Okay, very good. One last thing I wanted to mention, and this is almost on the topic of further reading, is the fact that of all I've given so far has been focusing on adjoint fields, but there is a very natural, at least to my mind, generalization of color kinematics to it in a double copy to theories which have matter. And all of this being relying on a representation of amplitude based on cubic graphs depends really on how much information you want your graph to carry. So here we're having adjoint theories, so we're having graphs which have just lines, right? Everything is an adjoint. I don't need to attach, label, dress the graphs with anything. But let's say that you have fields in fundamental and adjoint. The same game can be played, provided that you are careful. So now your graphs will be graphs like this. There will be, say, a solid line, and then there will be an adjoint line, which I represent like a gluon. So I have to allow for different lines. At tree level, for example, there will be something like this. So this is matter in a representation which you can pick up as the fundamental, but sometimes it makes sense even to have different representations than the fundamental. You can even make sense to impose some properties, and this is the adjoint. Then the same game can be played. What are the relationships that you find between color factors? Well, color factors will have algebraic relationship which now depend on the commutation relation of the matrices, right? Because the color factor corresponding to this will be, will be made of strings of representation matrices. They commute according, giving you structural constants times another matrix. And these are algebraic relations which are just, morally speaking, exactly the same as this. The only ingredient which is missing to having a very nice, simple generalization of color kinematics duality is the pairing of the fields with a double copy. You have to tell me how you are pairing fields to give you a supergravity or a gravity theory, and in particular, you have to tell me, are you going to allow this graph to be double copied, say, with this graph? The answer I would give is no. I would say that graphs which are identical, keeping into account the fact that different lines now are drawn in different ways, should be the ones which get double copy. A more elegant, perhaps, way of phrasing this is that I associate a gravitational state in a double copy theory to each gauge invariant bilinear of gauge theory states. So I impose, for example, that whatever the representation I have in the gauge theory on the right and left of the constructions are conjugate to each other. And then adjoint goes with adjoint, and then build my gravitational states as gauge invariant bilinears in this way. You can see this is a very basic extension, and you can see this already in the review. Conceptually, I don't think there's any extra element. But it's a very nice extension and gives you a huge amount of freedom. And this has been key in sort of extending a double copy to more and more gravitational theories. This is the first one. Then another thing I should mention, I had a note about talking about string monodromy relations, but you have asked before, so I switched the order. If you wanna, I mean, one part of these lectures that have not been, in my mind at least, sufficiently detailed has been multi-loop calculations, and the reason for this is that it's very difficult to put that on a blackboard. You'll find a little bit more on the review on this. And finally, I would mention the fact that there is the double copy, and then there are manifestations of the double copy. So there are many flavors. Here I have, in a sense, privileged the BCJ formulation on the account that is field theoretical, easy to introduce, easy to motivate. But historically, for example, the KLT string theory perspective has been dominant. And there are others, formalism, modern formalism of amplitude, for example, the CHY formalism, scattering equations, that have the double copy as a built-in feature. So let's differentiate a little bit between the double copy and the version of it. It's a more general property, but it takes many forms. All right, so I think this is a good time to stop. As I said, I will keep updated the Google Doc, the Google Drive for adding some references. I hope I remember every references which has been asked to me. In case I forgot something, please shoot me a line. Thank you very much. And yes, you have a question, a very pressing question. Yes. No, please, it's fine. I was finished. Mm-hmm. This is a very good question, and the answer is to me that in this formulation is a little bit unclear for the following reasons, but there is a fundamental reason why it is hard. The fact that this formulation with the structural constant doesn't like large n. And heuristically, and here, I hope I don't sound too hand waving, is it makes sense that this is the thing that would enter a double copy because amplitudes in gravity, they are like planarity of the amplitudes. I mean, the ordering, planar, non-planar, it is something that you don't want in gravity. The amplitudes in gravity don't have that organization coming from large n expansion. So if I want to construct amplitude in gravity from gauge theory data, I prefer this organization for the Fs. A consequence of that is that it's not so easy to talk about large n in this particular case. And a lot of the progress which has been done in the analysis of super EML's theory, of course, depends on that. So this is a place where there is a little bit of tension. Yeah, very good. Other questions? Otherwise, yes, please.
I mean, you mentioned also that there is a web of double copies.
Mm-hmm.
Some of them do not even include gravitational theories.
Mm-hmm.
So can you make can you make an example or even
Mm-hmm. Yes.
where the double copy doesn't work?
An example where it doesn't work. Okay.
It's a vague question, but I'm sure you understand.
No, yes, it is in a sense. It is in a sense a difficult question in the sense that there's a number of gravitational theories which, at the moment, I don't have a good candidate for a double copy construction. That it doesn't work, and also I can come up with a series of double copies which are pathological, right? I mean, the most elementary example of a double copy that doesn't work would be if I don't impose some color relations, and then I end up having an amplitude which is not invariant under linearized diffeomorphisms. So one of the a while ago, you asked me this question, I would say, well, Einstein gravity, right? But then there's this extra construction which involve ghosts. So if you are willing to buy that, then I will say, well, of course, then it still works. But at the moment, there are a number of theories which I really wish I had a good double copy construction for, and I don't have at the moment. One of these is, say, n equal to 2 supergravity theories in which the scalar manifolds are not non-homogeneous states. Non-homogeneous manifolds, sorry. In that case, there is not like a good I mean, there's not yet, it has not been yet formulated. Okay. Another, well, I mean, I think this is, I think this is in a sense where the boundary between what we know and what we don't know are. So n equal to 2 theories which don't have homogeneous target spaces. N equal to 2 theories which don't uplift to 5 dimensions, because n equal to 2 supergravities are much simpler if they uplift to 5 dimensions. So purely, and then n equal to 1 theories, we know that there's a huge amount of supergravities there, but we don't have explicit construction for all of them at the moment. So again, this is more of an area of current research than a situation where the construction by itself fails. But one thing I have learned, sometimes painfully, is that the gauge theories that enter a construction can be very hard to work with. So at some point, I can see, if I want to be a skeptic, I can see a situation where the complexity of having both a gauge theory, which gives you the desired supergravity theory, and a representation of amplitudes, which obeys color kinematics duality, becomes so large that perhaps I just do stuff with the supergravity directly and not use the double copy. That is also a possibility. Okay, very good. Any other questions? Otherwise, I think in the interest of facilitating the next lecture, we'll stop it here. Thank you very much one more time for the opportunity.